So good afternoon. This is CIVE 634, Surface Water Hydrology, and this is the second class of a second week. And the subject today is going to be evaporation and evapotranspiration. Hopefully we'll get to evapotranspiration. Can you see the green page?
Yes.
Okay, so we're ready to work then. So this is, by the way, is my hydrology book, which I have as a reference for you as part of your reading material. And the reason why I do that is because, okay, here we go, is because I have to give you some background information. Now, let me say this. The subject today and next Wednesday is evaporation. Evaporation together with evapotranspiration. The difference is that evaporation is from a surface that has no plants. In other words, evaporation proceeds without the benefit of plants, while evapotranspiration is the evaporation that happens through plants. Now, these two processes are similar. They're not the same, but they're similar. They're somewhat related, and sometimes formulas that were intended to do one are used for the other. So we'll get there. We'll learn how all that stuff it pops up and puts it. We can put it together. Now, at the outset, I should say that our job here is to cover the Penman-Monteith method and its somewhat recent sequel, the Shuttleworth-Wallace method. But we cannot do that without talking about the Penman method, which is the first method, the first conceptual method that was developed in the year 1948 by Mr. Penman. But typically I cover that in an undergraduate level, at the undergraduate level. However, I do realize that many of you, if not all, have not taken an undergraduate hydrology. So I felt that it was necessary that I briefly talk about that. So I'm going to kind of review this subject for you. And I know for some of you may be the first time you see it. And that's what I'm going to go a little fast, but not too fast. I don't want to leave you out there hanging in the lurch. So I'm going to go over and cover the basic material on evaporation. And we start in here. Let me just pop this up a little bit so you can see it a little better, right there. Can you see it a little better now?
Yeah, we can.
Okay, so evaporation is the process by which water accumulated on the land is converted into vapor state and returned to the atmosphere. Let me say at this point, because we already studied water balance. The water balance is the accounting of precipitation into its components. But the global approach of water balance says that precipitation is going to go into runoff and into evaporation. As a matter of fact, on a global basis, about 30%, 30 to 35% of all precipitation on a global basis, global terrestrial, because one global terrestrial is not the same as global, because global includes precipitation in the oceans, and that basically, from a hydrology standpoint, we're not interested because we're not profiting from it. We can't use it, right? So evaporation then refers to the 30, 35% runoff, and the rest, which is 60 to 65%, would be evaporation. So evaporation, the total sum of evaporation on a global basis constitutes about 2/3 of the water that evaporates. That's the way Mother Nature put it together. She designed it that way. Of course, that number, let's say 30%, let's just a round number, that 30% varies. It's a global average, but it varies between, I think I mentioned values of 2% in the very arid areas, and I've also mentioned a specific value of 93% in a very wet area in the Philippines. These numbers were quoted by Leibovich in his book. So it does vary widely. So it is our job really as engineers, given a site, which we're always given a site, we're told you're going to study this watershed, however small or big it is, for the water content, for the water resources, so that we can hope to use the water to our advantage. Okay, so that's the concept. It is expressed in millimeters per day, centimeters per day, or inches per day. Typically, when we convert from inches per day to metric or SI system, we jump the gun in here and go to millimeters per day because of just usage. But we could also speak in terms of centimeters per day. As you know, centimeter is 10 millimeters equal 1 centimeter. There are several meteorological factors that affect evaporation. And here I list those that are important from our standpoint, engineering hydrology. Net solar radiation. The solar radiation is is the basic driver of evaporation. But there's also saturation vapor pressure, the vapor pressure of the air and water surface temperatures, wind velocity. Wind is absolutely essential for evaporation to continue. The molecules have to be put into the air and then removed so that space could be made for other molecules that are still have not evaporated. And atmospheric pressure also. And you know, atmospheric pressure varies on the surface of the earth between the maximum number at sea level, and then as you climb up in altitude, the atmospheric pressure starts reducing. As a matter of fact, the pressure at about 4,000 or 5,000 meter altitude is about only 70% of what it is at sea level. So these are the variations. Now, what's the range of evaporation? That's a good question. And I have not shown everything here in terms of the world because we don't have that kind of data. But I can show you what NOAA has put together in terms of the evaporation rates, average evaporation rates throughout the United States, which is a good example. United States, as you can see, has, as we know, has some very wet areas, not tropical, but very wet. Actually, there's an exception to this because there's a small tropical area in Puerto Rico. But Puerto Rico is considered to be, it's not a state, and therefore you can say it's not within the conterminous United States. But Puerto Rico has this very small tropical area out there. But excluding Puerto Rico, we have in here wet areas and dry areas. And as you can see, that correlates very well with the amount of evaporation. Evaporation is highest in the dry areas and lowest in the wet areas. So it follows that if you look at this chart, the darkest 10 to 20 inches per year is in the Pacific Northwest, a very small corner out there. It must be very wet in the state of Washington. Can you see it? Can you see this area over here?
Yes, we can see it.
Okay.
Yeah.
And over here, the driest, more than 80 inches per year, is over here, right here. What part of well-known part of California is over here, by the way? Can you guess? Or
Is that the Salton Sea area?
no, it's not the Salton Sea. It is Death Valley.
Oh, Death Valley. Yeah.
Death Valley, right at where the arrow is Death Valley, roughly. A very, very arid area.
It's aptly named.
That's why they call it Death Valley. Okay, so this is a very good explanation of the amount of evaporation. So if you're out there doing some calculations and you're completely off this chart, then you're probably wrong. Okay, because this is the general tendency of evaporation in the United States. Now, there are various ways to calculate evaporation. We must calculate because we're always attempting to figure out how much water can we use in a watershed, and evaporation is important. Also, I must say at the outset that the plants evaporate water, and that's called evapotranspiration. And we cannot do what has been done in the past, which is to pretend that the plants don't have the right to the water that they're evapotranspiring, and we can get rid of the plants, basically kill them, and then try to use the evaporation that or the water that they would have evaporated. That looks good on paper, but it backfires. And I can tell you stories, and I will get to the basic story on that. Can't do that because if you do that, eventually you change the albedo, and the albedo changes the entire local weather, and then all of a sudden you lose the plants and you lose the rain. So if you lose the rain, then it is counterproductive because you were counting on the rain that the plants were producing. You see how it works? Okay, so we'll come back to discuss that very complex issue later on, and I even give you an example of what I'm saying here. But at this point, there's various ways to calculate evaporation, various methods. A water budget based on volume, an energy budget based on energy, or a mass transfer technology or methodology. The mass transfer methodology was developed originally by Dalton, working in the UK. I believe I had said before it was in the year 1803, but I'll check that later on. We will mention Dalton in this piece of work that I'm reading. Okay, so first we talk about water budget. Now the water budget is a method, and the basis of the water budget is this equation over here. It's a volumetric accounting of where the water is going. E is evaporation, P precipitation, Q surface runoffs into the reservoir. Typically, a water budget is used for reservoirs, for reservoir evaporation. So all this makes sense because you're accounting basically for where the water is. But like I said, this is for reservoir or lake evaporation. The energy budget, though, can be used anywhere, not just necessarily lake. You can use for evaporation, for evapotranspiration. So the energy budget turns out to be a more flexible method, and that is the most common or the more common method to calculate evaporation. Now, there's various ways to do this, by the way. The energy budget is popular simply because it is the basis of the Penman method. And subsequently, as I think I've already told you, the Penman derived or developed into the Penman-Monteith in 1966, and then FAO of the United Nations, the Food and Agriculture Organization, adopted the Penman-Monteith method as a standard for use throughout the world for irrigation projects, for developing evapotranspiration studies for irrigation projects. So that's why energy budget is important, because it's the basis of the Penman. That is the basis of the Penman-Monteith. And now we're going to be talking later on next time extensively about the Penman-Monteith method, which is the one that the method we must stress, because that's the one that you're going to be using. If you get involved in these calculations, the first thing they're going to say is Penman-Monteith. Okay? So we'll get there. Now, but here, when we look at energy budget, we typically get into a combination of what's physics and chemistry. And engineers are kind of good with physics, but mostly the mechanics, because we study 3 or 4 classes of mechanics at school, civil engineers, but we don't get to the other part. So we're a little bit rusty as far as that is concerned. Not that it's too difficult or too easy for that matter. So I'm going to get in there today just to describe it, okay? To describe the issue first of radiation. And then later we'll talk about the actual vapor pressure, which is chemistry. And you know that engineers, civil engineers in particularly, not environmental engineers, are a little bit weak on chemistry because we perhaps took only 1 class at school. So the first thing we need to look into is where is the origin of this thing? Radiation is the emission of energy in the form of electromagnetic waves from all bodies above 0 degrees Kelvin. So every body emits radiation, only that the radiation from the sun is so much that it feeds us, or it feeds energy to us on a constant basis 12 hours a day, because the world rotates, and as it rotates 12 hours in the equator, in the lower latitudes, 12 hours sun and 12 hours night or dark. So the solar radiation is received on the Earth's surface, and it reaches the outer surface of the atmosphere in a nearly constant flux of about 1.95 calories per square centimeter per minute. That's the flux, meaning the discharge of energy through a cross section. That's called flux, that goes through in the Earth. Now, look at what it says in here. It says nearly all this radiation is of wavelengths in the range 300 to 3,000 nanometers, with about half of it of wavelengths in the visible range, 380 to 740 nanometers. So look at the electromagnetic spectrum over here. Gamma rays, X-rays, ultraviolet, infrared, radar, modulated frequency, TV, shortwave, I believe this AM radio. AM stands for amplitude modulation, I believe. Yeah, this is amplitude modulation, and this is frequency modulation. That's a radio. But for our purpose, the part over here, which is called the visible range, can be expanded into the colors of light. And light has colors. These are the colors of light. That's why we have the rainbow. If we have the atmosphere and it starts raining and there's sun, then the sun energy or light is diffracted by the rain, by the raindrops, and it creates the rainbow. So you can see these are the colors of the rainbow from ultraviolet through infrared. The ultraviolet are shorter, and the infrared is longer, as you can see. This is a reverse scale, and that's the reason why we can see red faster than we can see green, and that is the reason why the traffic lights are red and green. Red, so you can see it very quickly because they want you to stop. In green, you don't have to see it. So green, if the light is green, then you can go ahead. You have the permission to go ahead. Okay. And that is the reason, this is interesting, that is the reason why some people think that maybe if you drive a red car, the other people will see you a lot faster than if you were driving any other color of car. Think about that, because it does make a lot of sense. So there's some advantages of driving a red car. The advantage is that it's less likely that people are going to hit you if they didn't see you, because they're going to see you immediately, right from the start. Okay, so that's a little bit of an application on the issue of physics related to color. Now, as the solar radiation passes through the atmosphere, it changes in flux in its spectral composition. The fraction of the radiation that reaches the Earth's surface is called direct solar radiation. But the radiation is also scattered by the atmosphere that reaches the ground. That's called sky radiation. So for scattering and then reaching the ground, the radiation that came from the sky, indirectly, not directly from the sun. And the sum of direct solar radiation and sky radiation is called global radiation, and that's what we're going to use in order to do our calculations. Now, here we defined a very important concept, albedo. I consider it to be the fundamental parameter of physics, and I'll explain why. What is albedo? Albedo is the reflectivity coefficient of a surface towards shortwave radiation. The coefficient varies with color, roughness, and inclination of the surface. Its value is for 3%, 0.03 to 0.10, so 10% for water. 0.05 to 0.30 for vegetated areas. So green areas have low albedo. 0.15 to 0.4 for bare soil like deserts, and up to 0.95 for snow-covered area. So this kind of explains what happens in nature. If you have an area which is snow-covered, it has 95% reflectivity, therefore only 5% of the energy remains, and there is too little to produce or provide any transformation that is required if any life is going to be produced. It's mostly vegetated life. We're not talking about animals at this point, just vegetation. On the other hand, if you have vegetated areas, that means to 5 to 30% of reflectivity, meaning lost. That means there's 95 to 70% energy that is being kept by the ecosystem and allows the transformations that occur at the vegetation level. So as you can see, this makes a lot of sense in terms of what actually happens out there in nature. So this is a table of typical values of albedo. Why did we bring this up? We must bring it because it's part of the energy balance. However, it's also very important for us to consider Albedo is a fundamental parameter, and we all should understand exactly how it does and what changes are there in albedo as far as the world is concerned. And I pulled out this graph from NASA, global distribution of albedo. The reds show high. So here, look at this is the Sahara. The Sahara. And over here we have in Upper Canada, apparently high albedo. It must mean there's ice in there. But everywhere else, and this is not a very high resolution picture. That's all I had. That's all that was given to me by NASA. But as you can see, there are some very clear things in here. For instance, let's take a look at Europe. Europe is nice. You can see there. In Europe, in this area over here, it's about like maybe Poland a little bit of Russia. Okay, it is a little bit high, but not too high. The values over here, the green values and the blue-green values are the ones that are good in terms of low albedo that will make possible lots of vegetation. I'm kind of surprised, to be honest with you, as I looked at this figure this morning, that the Amazon rainforest is not showing a little bit darker. I mean, I will have to blame NASA for that. On the other hand, take a look at China. China has two major regions, climatic regions. The eastern region is all very low albedo, which is good. And the western region is very high albedo over here. This is the Gobi Desert. That's not good because in terms of life, there must be very little life out there. So China does have. The United States, go back to the United States. The United States has nice areas here all the way up to like the 100 parallel, and then it starts getting a little bit red in here, high albedos, right? And over here in Arizona and Eastern California, we have very high albedos. But in the north, that's Washington State and Oregon, the albedos are much less. So you can see this kind of matches exactly what's out there. There's also the balance or the radiation budget is a very complex thing, and I'm not going to bore you too with it, but I do want you to take a look at this chart later on. Now, in the energy budget, the incoming energy can be expressed as this formula, 221. Q sub I is incoming energy, Q sub S, global radiation, which is 1 minus the albedo. A would be the albedo. So the albedo is reducing the amount that is retained, the amount of energy that is retained by global, or rather the global radiation gets reduced by the albedo. Then we have long wave radiation lost by the water body and net energy advected into the water by streams, rain. So this is a complete balance, but in reality, in practice, we simplify that. The energy expenditure is this. Incoming energy expressed as Q sub O is the energy expenditure, the use of energy. Sensible heat transfer from water body, energy spent in the evaporation process. Right, evaporation is going to use some energy. So we need to calculate that energy and convert that eventually by a very convenient formula to depth, because depth is what we're interested in, volumes of water. And there's a direct relationship between the energy and the depth, which we'll take a look at in a minute here. Okay, so we have evaporation when the evaporation is positive, and if the reverse process, then it's called condensation. And condensation is also very important, by the way. In hydrology, we have five sources of water, and one of them is the condensation that takes place under certain climatic conditions, because the condensation of the air leads to runoff, and the runoff can feed water to the plants. We have called that in research, we have called the so-called horizontal precipitation, which is a precipitation that nobody sees, but it produces runoff. How fascinating, isn't it? Again, horizontal precipitation. I have a paper on that. I'm going to see if I can make it available for you so you can take a look at and where the research is these days. The research is actually in the amounts of horizontal precipitation. A case in point, the high trees in Northern California, the coast of Northern California, has a lot of precipitation, about 100 inches per year. but that is supplemented by the horizontal precipitation. And that's the reason why those trees are the largest in the world, tallest and largest in the world. Let me repeat that. In Northern California, along the coast, we have some of the largest and tallest trees in the world, taller than the Amazon. Yes, the Amazon rainforest, the canopy or the elevation of the canopy in the Amazon is about 60 meters. So that's about 200 feet. And the elevation of the trees that grow in the Pacific area of Northern California is 80 meters. That is 250 feet. So it's larger. And because of that, there's more volume to them. Interesting. So the largest trees, the largest tree ecosystems or tree ecosystems are not in the Amazon. They are in California. Okay, let's go back now to this equation 223. 223 in here says that you can take the evaporation and we can convert to the evaporation energy or the energy in evaporation, the energy used in evaporation in calories per square centimeter per day can be converted to equivalent evaporation rate in centimeters per day by this formula. And this is the formula that we're going to use in our calculations right now, later on. Energy equal rho, the density of water in grams per cubic centimeter. Lambda is the heat of vaporization, a function of the temperature. We have to go back to our appendix over here. And I made this clickable, so it's fine. And E, evaporation in centimeters per day. If we go back in there, that is where we are going to click over here. Unfortunately, let me try that. Yeah, that's right. I did the right thing. Yeah, I did the right thing. I put a target in the HTML code. Okay. Okay, the terms Q sub H and Q sub E. Now what's the difference? Q sub H is the sensible heat, and Q sub E, the energy spent in the evaporation process. What is this? Q sub H, sensible heat. That's the heat that's coming out of the ground because it's heated. And Q sub E is the heat that is coming through the evaporation. So there's two parts to this whole thing. To the total energy is separated into Q sub H and Q sub E. Now these are difficult to evaluate directly, globally and locally, or regionally. Fortunately, we have Mr. Bowen, who, by the way, was Californian. He, I believe, was living here in San Diego many years ago, maybe roughly 80 to 100 years ago. I believe that it was him who became at one time and functioned as the director of the observatory at Palomar. So if and when you go to visit the Palomar Observatory, which is a couple hours from here, where we are right now, check it out and see what they say about Bowen. Now this Mr. Bowen, great guy, came up with this relationship, number 224. He developed this relationship, and that's what we call the Bowen ratio. The Bowen ratio is the ratio between Q sub H and Q sub E. Q sub H and Q sub E of the total energy, which kind of determines or characterizes the climate. Because the more vegetation, there's a certain humidity to it, and then the Bowen ratio changes. Otherwise, if you go arid, then the Bowen ratio also changes and it decreases. I believe it decreases. So this is the Bowen ratio. The gamma is a psychrometric constant that was developed by Bowen, or he had a lot to do. I'm not exactly sure whether he actually developed the parameter, but he put it into his formula. He must have had a lot to do with it. I'm not quite sure of the history of this whole thing, of the development. But I know that this is the formula that is regarded as Bowen's ratio. The gamma is a function of the physical properties of dry air, varying slightly with temperature. T sub S is the water surface temperature, T sub A overlying air temperature, E sub S saturation vapor pressure at the water surface temperature, and E sub A is the vapor pressure of the overlying air. And P, atmospheric pressure in millibars. Now, when Penman did his work, it was very convenient for him to assume that P was 1,000 so that he could get rid of this part over here. This is interesting because the actual value of P in millibars at sea level is 1,002. So very close to 1,000. And given all the inaccuracies typical of these calculations, we would probably have to assume that P equal to 1,000 didn't mean a whole lot of difference, unless of course you were going up the mountains, like the mountains in Peru are extremely high. You can get altitude sickness if you head out there without any experience and so forth, in which case you are breathing less air, right? 70% of the actual amount of oxygen, and therefore there would be a problem in the calculation. But as long as, and that is why the calculators attempt to get information on the atmospheric pressure, so they can do that. They can put that into the calculation in here. Let's keep going on in here. And I do realize some of you are saying, what the heck is this? I never heard it. Well, that's why you're here, to study all this stuff. Now, when we do a balance of the incoming energy, and incoming energy is equation 221, and the energy outgoing, the expenditure of energy, it takes us to equation 225, which is the total and complete equation. Okay, the mass transfer approach is the first approach that was done by Dalton. And I'm not sure, I did say 2000, let's take a look at this. Let's get ahead in here. No, I don't have it in here for some reason. I don't have it in here for some reason. Well, that's fascinating. Okay. But the mass transfer approach is basically due to Dalton. And that is the easiest way of doing this calculation, but it is limited because it's empirical. Empirical means, remember I mentioned to you, there's 4 levels of hydrology. Hydrology deterministic, then the stochastic, then conceptual, and the fourth is the least, I guess you could say the least developed formula is the empirical equation. So we should consider the mass transfer somewhere in between. It's quite not empirical, but it's not quite conceptual either. So it's kind of like 1.5. Out of 4 levels, 1.5. It's not 1, it's not 2, 1.5. So that, due to Dalton, 1803, and I'm not sure exactly why I don't mention Dalton in here, but this is the point that the calculation, the mass transfer calculation is done in this way. Oh, here it is. Here it is. I'm sorry. I didn't have it. The recognition that the evaporation rates are dependent on the water surface temperature and the atmospheric pressure led to the mass transfer approach of Dalton. So the formula by Dalton is equation 226. He said evaporation is a function of the wind, undetermined function of the wind, times E sub S minus E sub A. Let's take a look at the parentheses first. E is evaporation rate. Well, F sub U is a function of the horizontal wind speed. Undetermined yet. He just said this is what's going to happen. You got to put in there a wind speed. And E sub S, the saturation vapor pressure at the water surface temperature, and E sub A, the partial vapor pressure of the overlying air. When the air is saturated, that is when the relative humidity approaches 100%, E sub A is nearly equal to E sub S, and the evaporation tends to 0. In other words, under atmospheric relative humidity 100%, there's no evaporation. If it were 0%, there would be a lot of evaporation, like in the case of a desert. A desert, there's very low evaporation. And I'm sorry, there's very low humidity, relative humidity, and therefore quite a lot of evaporation. As a matter of fact, we have a calculator to do that, and I'm going to have you do that calculation as part of your homework later on. Again, I do say or state for the 3rd time that we have these calculators that are doing all these methods. Just about all methods that we could put our hands into or get our hands into have been programmed and put into a calculator. I think I mentioned that we have more than 300 calculators in our laboratory. So obviously, we don't necessarily require that you go through all these calculations by hand. You could use the calculators because it's very safe. Another thing you could do if you wanted to is you use your Excel sheet and program everything in your Excel sheet. A lot of people feel very comfortable with this procedure because they're very good with Excel. They become, over the last 10, 20 years, good with Excel, and they feel that they must or they have to use it, and which is fine. I have no problem with that. Whether you do it by hand or Excel or my calculators, it's fine, as long as you get an answer. I do recommend the calculators because it's going to get you to do the answer in 5 minutes instead of an hour. Okay, so several empirical formulas of the Dalton type have been developed over the years. They are collectively referred to as mass transfer equations, and a commonly used mass transfer equation is that of Meyer, which is this one. And you can see that it has a wind function over here, but it is empirical. It's got a 1 and a 10, which we don't know where they came from, right? So this is an empirical equation of the Dalton type. So look at the difference between Meyer and Dalton. Dalton said the evaporation is going to be an undetermined or undefined function of wind. And Meyer already determined that function to be this quantity between brackets over here, and a coefficient, which varies between 15 for small ponds and 11 for large lakes. Small ponds having more evaporation and so forth. So this is a 1.5 in our hierarchy of methods. It's kind of empirical, but it's also kind of conceptual because it's based on the concept by Dalton. Another version of the Meyer equation is the next one. And the difference is that equation 227A is in inches per month, while equation 227B is in inches per day. But it's kind of the same thing. Other Dalton type evaporation formulas are given here. Lake Hefner evaporation studies, as you can see, arbitrary or rather empirical wind functions in here. Empirical wind functions, because this says that E sub S minus E sub 2 at a certain elevation times this empirical number 0.00304 times V4, which is the velocity. It's the velocity, yeah. The velocity of the wind at 4 and 8 meter heights. So these are empirical formulas. And like I said earlier, I've mentioned in here 4 formulas, but there is at least 30 or 40 formulas. If you go to the manuals of hydrology like Chow's 1964 or Meidman 1993, they will have a chapter among the 30 chapters in each one of these manuals on evaporation, and they will list all the available formulas. So it will be a tough decision to decide which formula to use. And the answer, I think, is very clear at this point. We really have a tendency not to use these formulas unless we must. The formula that we use is either Penman or the better formula, which is the Penman-Monteith. So we'll get to that later on. Why is the Penman-Monteith not used everywhere, period? And the answer is that it's got a couple of parameters that are a bit difficult to determine. So that is why not a lot, but some people shy away from Penman-Monteith. I know that for a fact. Back many years ago, we were doing a study or an evaluation in Florida, and it came about, or I found out that there was a lady over there that had developed a local model of evaporation because they could not get the parameters for the Penman-Monteith. Therefore, they figured something, a local model meaning it's some empirical model that they developed based on data, and it applies directly and only for the local conditions of Florida. So I say this to give you an example or to show you that not everybody out there is blindly using the Penman-Monteith. That is a fact verified by experience. Okay, so when we have these methods, when we combine the methods of energy budget, which I already talked about, and mass transfer of Dalton, we get to a method that is called a combination method. And Penman was the leader of the methods, of the combination methods, because he started developing them around 1948. Let me take a look at this. It says in the Penman 64. And if we look at 64, here it says Penman. There's a mistake in there. I have to fix that. Penman 1948 was the original method that he developed. Can you see there, Penman 1948, 65? So I'm going to have to fix that. The reference is a little bit off, and that happens. Bugs are always there. Okay, so with Dalton formula, okay, here's the Penman formula. This should be 65, not 64. I'll fix it later. So Penman came up with the energy balance. Then he put in there the Bowen ratio. And once he put in there the Bowen ratio, he came up with this formula, converting Q to E by using that formula 223 that I already told you. So converting energy to depth to evaporation rate. And then assuming that P is equal to 1000, which I told you is very close to 1003, which is atmospheric sea level. Actually, I did say 03, but I was wrong. Is 1013.2 millibars. That's the atmospheric pressure at sea level. It's 1% off from 1000. And then it reduces to B, which is, that's the expression for the simplified expression for the Bowen ratio. Then what Penman did was he developed this ratio, which was called a saturation vapor pressure gradient. He developed this ratio from experience. He knew what he was doing, obviously. We have read the paper by Penman, remember? So he developed this ratio delta, okay? And he developed also this ratio 234, which relates the E sub A, the ratio E sub A over E, which is the ratio of mass transfer evaporation to the total evaporation. The mass transfer evaporation to the total evaporation. And he was able to write it in these terms. And then he went ahead and combined all these three equations, 32, 33, and 34. No, 31 to 34. There's four equations, 31, 32, 31, 32, 33, and 34. And he ended up with this equation 235, which is really a weighted function. It's a weighted function because it has two weighting parameters. Penman's delta and I guess you could say Bowen's gamma. And he basically said that there was going to be a weighted function in here depending on the values of delta and gamma, and the total evaporation was going to be a combination of the evaporation due to net radiation, which is E sub n, and evaporation due to mass transfer, which is E sub A. Basically, what Penman said or did was that he said it is not enough to use the E sub A of Dalton. We're going to combine it with E sub n that he brought in from the energy concept, and he came up with a combination method. It's a combination method of those two methods, the mass transfer and the energy. Interestingly, though, in order to come up with this equation, he had to combine equations 31, 32, and 33, and 34. And in the past, I actually had to prove this equation. So I spent some time when I was young, maybe 30 years ago when I was writing the book, back in the middle 80s, that was 35 years ago, I spent some time trying to be Penman. And I say sometime kind of jokingly a little bit, because it took me a while. I don't recall, but it must have been at least 3 hours. And I was good at that time with algebra. But it took me about 3 hours to prove that Penman was correct by combining. It was an algebraic exercise, a combination of equations 231, 32, 33, and 34. Since that, I put that as a problem in my book. If you go back to my book, chapter 2 of my book and go to the back, the examples of the problems. I believe problem number 41, if my memory serves me right, it says prove equation 235. Since doing that, every once in a while, I got kind of mean and asked the students to do that. But I don't do that anymore because I feel that it is sometimes an exercise in futility. It's pure algebra. So if you're good with algebra, you could do it. But it will take you some time, as it took me when I was young. If you wanted to do it on your own, I'm not going to ask you, and I don't think you guys are going to do it, because you're going to have 3 or 4 hours out there laying around so that you can use it. But if you're challenged by a tough project, this is a tough project to prove that 235 comes as Penman arrived to from the combination of 31, 32, 33, and 34. At any rate, this is a conceptual method because it's a combination method based on one deterministic energy problem, or rather approach, in another which is conceptual, kind of empirical. So the combination of empirical and deterministic ends up being conceptual. So that was Dalton's method. I'm sorry, Penman's method. How do you calculate delta? There are various formulas for that, but we looked in the literature and came up with this one, which is relatively easy to calculate based on T sub A, which is the air temperature. You want to look at the air temperature formulas that have the air temperature because it's easier to get the data for the air temperature than the data for the water temperature of the reservoir. So this formula is used, or we used it here, we used it in all our models, the delta, and therefore you can proceed to calculate Penman's method if only you knew the E sub n, which can be calculated, the E sub a by some kind of Dalton formula, and you calculate the gamma and the delta. The delta with the formula for 236, and the gamma has a specific way of calculating it. Furthermore, we also have the equation 237, which is a simplification of 236. And table 26 gives us the values of alpha for the given gammas, because gamma is not a constant, it does vary. Gamma is called the psychrometric constant of Bowen. I believe, I'm not going to say it is of him, but it is included in Bowen's formula. That's gamma. Later on, we'll deal with this subject because I had to research this subject because when I did the calculators, since the gamma varies with the temperature, and as you can see, the influence is about from 65 to 68, is about 5%, right? 65, yeah, it's about 5%. And 5% to me was a little bit too big to admit that we were making a mistake. So I proceeded to study this problem, consult the literature. You got to go into the physics, the chemistry. And we came up with in precise determination of the variation of gamma with temperature of the air, which is explained or described over here. And once we have that, all we needed to do is have the calculator ask the user, what's the T sub A? And if this is your T sub A, this is your gamma. And we can even interpolate because we have, as I think I mentioned to you, the piecewise linear interpolators built into the model. Okay, so all the stuff can be done, and it has been done in the calculators. Okay, finally, at the end of this section, we say, other Penman type equations have been developed over the past 50 years. For instance, the National Weather Service has developed a Penman type equation for estimating evaporation based on mean daily air temperature and dew point, wind movement, and solar radiation. We quote the references. More recent examples are represented by the Penman-Monteith and Shuttleworth-Wallace. Penman-Monteith is 56. I'm hoping that I'm not going to. Shuttleworth-Wallace is 74. Let's say 56 over here. Yeah, and the 74 is the other one. Yeah, there's still a bug in there. I have to fix this stuff. I have to go over and fix it. The references are off a little bit. There's one off because the Shuttleworth-Wallace is 75. So the Penman-Monteith that was 64 should be 65. Correct. So I'll make those corrections in there. Can you believe this? Small errors in references continue to pop up. Okay, so now we're going to do an example in here. Calculate the evaporation rate by the Appendment method for the month of January for the following atmospheric conditions. Standard atmospheric pressure. That's the pressure. Standard atmospheric means at sea level. T sub A is 20 degrees Celsius, net radiation 550 calories per square centimeter per day. Now this number is given by the meteorological stations. It should be given by the meteorological stations. It does vary around that number, maybe 600, maybe 650, maybe 500, depending on the amount of radiation. Obviously, the closer to the equator that you're located, the more radiation, because direct radiation is coming up. Wind speed at 2 meters above the surface, 200 kilometers per day, and relative humidity is 70%. So then we apply the methodology, okay, the methodology over here, and I'm not going to go over there. I'm going to have you do it on your own. Make sure that all these equations make sense. And finally, we have the online Appendment, which we're going to run at this point. So it's 20, 550, 270. Okay, so it's 20, 550, 200 kilometers, and the relative humidity is 70. This is reversed in here for some reason. And the wind velocity is 200. I should have put it in order. And the month is January. Okay. So we have monthly ET is 23 centimeters. Daily ET, 0.7 centimeters. Is that easy? This says ETO. What does the O mean? Let's take a look at that. We will follow with that. So 23 centimeters, so that's exactly what we came up by doing this calculation by hand, and we also did it in the calculator here. So we are correct. We have run the online Appendment calculator and got the right answer. But we still have to answer the question of what is the O, the ETO. That is called potential evapotranspiration. Potential. Because there's two types of evapotranspiration, potential and actual. That is a very important subject because the potential evaporation is the only one that can be calculated. The actual evaporation cannot be calculated. It would depend on the local weather and all sorts of local conditions. So how does one estimate actual evapotranspiration? The only way to do that is by measurements in the field using an apparatus which is called a lysimeter. So a lysimeter is an apparatus designed to measure actual evapotranspiration. For lack of a measurement, the only way we could do is to calculate the potential by using any of the many formulas that are there to calculate potential evapotranspiration. As a matter of fact, there is no formula that can claim to calculate actual. All formulas say evapotranspiration, they actually mean potential because that's the only one that can be calculated based on data. The actual evapotranspiration would vary locally because it would depend on the moisture. Why? What do we mean by that? Evapotranspiration evaporation is a number, but it will depend locally on the plant, on the weather, and so forth. So therefore, there is going to be a variation between potential and actual, and that should be made clear from the start. It's a very fundamental concept. Okay, now let's proceed in here. Evaporation determination using pans. So, if we cannot do the calculation, can we build a pan out there and put it outside and return next month and see how much it has evaporated in an attempt to measure an evaporation in the field? And that can be done, and it has been done. And the reason why is because some people say, well, we don't believe in the formulas. Besides, these formulas give us different answers. Which formula am I going to use? And this is fascinating because there's several formulas, some of them very well established, like the Thorne-White formula. And there are a couple of other formulas out there that are very much used, and they give you different answers. Typically, 50% would not be uncommon. 50% means that if a person gets 100 as an answer, another person can get 200 or could get 50, and it would not be uncommon. Which one of these is the better one? And the answer is, we don't know. There are some formulas that have a tendency to be more precise, like the Penman and Penman on teeth method, and that's why they are preferred. There's a formula out there that is easy to apply, not a whole lot of data requirements, but has a tendency to be off the mark, and that is admittedly the turn-weight method. I have to say that because we have tried that, and many people have tried that. So if you see the turn-weight method out there being used, be careful because it may be off by 20, 30, 50%. Now, what does 20, 30, 50% mean in practice? Well, I always say the following, which is an interesting and fascinating concept. I say, if you're doing hydraulics, you're allowed 2% error. Because hydraulics, the determination of the stage of a channel is a hydraulic problem. And admittedly, considering the fact that manning is to be determined precisely, then the 2% calculation or the 2% error is allowed. So in other words, it means that hydraulics is a very precise calculation. While hydrology is not. Hydrology, you have to decide on the variability. Rainfall varies in space, varies in time. Runoff, God knows how it varies. So there's a lot of variability and possibility for error in doing hydrologic calculations. So hydrologic calculations, in my estimation, based on practice, you can allow 20, 30% error. So if I had said that earlier that the turn-weight method could get a 50% error, that means that it's unacceptable because it's more than 30%. 30% is the error that you would normally assume or accept in hydrology calculations. You see what I'm saying? Okay, now furthermore, now I'm going to stretch this analogy a little bit further. What is the acceptable error in sedimentation calculations? And those of you that are paying attention, that are taking sedimentation with me this semester, should pay attention to what I'm going to say right now. What is the error or the acceptable error in sedimentation calculations? And the number is, surprisingly, 100%. In other words, there could be 100% error. If one of you has an error, let's say 5, or a result 5, and the other one is 10, I say, oh, both of them are good. How is that possible? Because there's a lot of variability in the computation of sediment transport and of sediment production. The variability is due to the fact that the physical properties of soils, granular soils, vary a whole lot. Example, infiltration rate. What is the range of infiltration rate in the real world? And the answer is 10 to the minus 0, or rather 10 to the 0 to 10 to the minus 12. 10 to the minus 12 will be the deep clays, and 0 will be the gravels, the coarse gravels. So there's 12 orders of magnitude variability. So how are you going to pin down a variability of 12 orders of magnitude? That's difficult. Up to 2 orders of magnitude will be fine. So how is it that we can possibly do hydrology in the field if we have 12 orders of magnitude? Well, nature comes in to help us. She does not put that variability together, meaning in close range in the field. If you have gravel, you're probably going to have a lot of gravel and not clay. If you have clay, you're going to have a lot of clay and not gravel because of the process of sedimentation. So the actual order of variability in the real world is only about 2 orders rather than the 12 orders of magnitude. Suffice it to say that if nature had 12 orders of magnitude, we couldn't do any calculation. Absolutely. We'd have to give up and forget about it. You can see how this thing works. Okay. So that's evapotranspiration determination using pans. As far as examples on the pans, I believe that I have in here. Let me just advance here a little bit. Right, examples of the pans. Pan evaporation models. This is a pan evaporation model. The basic evaporation model is PET, which is potential evapotranspiration, equal to K sub P pan coefficient and E sub P pan evaporation. And the K sub P is a coefficient that is determined based on practice. This picture here is the Class A Evaporation Pan, which is the Standard Evaporation Pan. I remember one time, many, many years ago, maybe 30, 40 years ago, I had to buy one of these for a project, and I believe I paid, if my memory serves me right, I paid about $400. And nowadays it's probably 1,000 or even more than that, because 30 years have gone by. So that's one. This is the other one. This is the Colorado Sunken Pan. This is a little bit somewhat better because it's sunken, so it's better. The boundary conditions are slightly better in order to simulate actual conditions, because the pan is sunk in the earth. So those are the two pans that I have been able to pull together for this book. Suffice it to say that the Class A evaporation pan is widely used. It's widely used, and widely used with this chart over here. Pan evaporation coefficient for NWS. NWS stands for National Weather Service, which is an agency of NOAA. NOAA stands for National Oceanic and Atmospheric Administration, which is in charge of the federal government agency or institution or umbrella, I guess you could say, in charge of the weather. Studying the reporting on the weather. So we have the relative humidity over here, wind speed, light, moderate, strong, very strong, in the coefficients, which, as you can see from the measurement, you have to apply a coefficient, which is K sub P, K sub P. And the lowest coefficient that you see in here is what? It's 55, 75, 85. So I can see a very high coefficient of 85. Do I see? Yeah, there's an 85 in there. And the low coefficient is about 45. 40. I see a 40 in there. So between 40 and 85% is the range, 40 of the actual measurement, is the range of variability of the NWS Class A pan, which is this one. So that's as far as the pan evaporation models. The pan evaporation models. So now we move on to evapotranspiration, which is the kind of the sister process, and the difference is that the evapotranspiration happened through the plants. I say with the benefit of plants. So the plants always need to evapotranspire to maintain the so-called turgor, Turgor. If you haven't heard that word before, now you heard it. To maintain turgor and not wilt. If they cannot maintain turgor, they wilt and they die eventually. So for the plant to remain alive, it has to have a supply of water, more or less permanent to an extent. Some plants can take a lot dryness, like cactuses and things like that. But all plants require a certain amount of water. And what the fascination of this whole thing is that the more water in the environment, which depends, of course, as you know, on the local weather, the plants that were adapted to the amount of water follow. Meaning, if you have a lot of water, you'll have plants that like a lot of water. If you don't have a lot of water, you would have plants out there that don't need a lot of water, like the cactuses and stuff like that, the plants of the desert. Does the water vary? Of course, it varies. It varies from the range I have not mentioned, but I should mention it at this point, and you should write this down. The lowest precipitation in the world is 0 per year. Never. It never rains. Where? In the Atacama Desert in northern Chile. Again, I repeat, lowest precipitation in the world, 0. 0 whatever, 0 millimeters per year. Per year, it's per year, measured per year. The largest or highest precipitation in the world, there's a discrepancy and there is a fight. In books, it says that it's at Cherrapunji in India, in Assam. I'm not quite sure if Cherrapunji is in Assam but it is out there in eastern India. And it has the record of amount of precipitation in the earth, 12,000 millimeters. In other words, 12 meters. So you go from 0 to 12 meters. That's green hell as far as I'm concerned. I actually haven't been there. Actually, 30 years ago, was it 30 years ago? Right, exactly 30 years ago. I had been invited to go out there for a project. And I was intending to go there because I thought I was adventurous, and I said, hey, I want to see that place because it's very, very wet. 4 times wetter than the Amazon. Can you believe that? The Amazon is already very wet. But fortunately or unfortunately, I was unable to get there due to that we didn't have the necessary permissions or the protocols in order to, for say, a quote-unquote foreigner to go out there and do a visit. So I actually never got to Cherrapunji. I intended to, but never did. At this point, I'm sure I'm not going to go there. Besides the politics and so forth. But the point is there's 12,000. And why do I say that there's a fight? Because recently there was a report that there is a very small area in Hawaii, in one of the islands of Hawaii, small area, localized point precipitation, which kind of is along the level, around 12,000 millimeters also. So that's considered to be kind of the alternate. But the difference is that that's a very small area in Hawaii, while the area in Cherrapunji, India is large. It's a large area. So the classical number is the Cherrapunji, or the classical data for the amount of rainfall. Now, evapotranspiration is interesting because that is the water that is coming through the plants. So what's the maximum and what's the minimum? And for that, we can use the calculators. You can impose on a calculator a very harsh situation intending to get the most evapotranspiration according to the formulas. And you will get some value. I don't recall at this point exactly what it is, but I think I put it in the homework. I believe I'll check that later on. But you can get, it's something on the order of 3,500 millimeters per year. 3,500 to 4,000 millimeters per year. And the lowest is about 500. So between that range, so lowest 500 millimeters per year and highest about 4,000 millimeters per year of evapotranspiration. That is correct, evapotranspiration. So the ranges in this whole thing. So evapotranspiration is the process by which water is converted into vapor state and returned to the atmosphere. It consists of evaporation from water, soil, vegetation, and other surfaces. In this sense, evapotranspiration encompasses all water converted into vapor and returned to the atmosphere, and therefore it is an important component of the long-term water balance of a catchment. Okay, there is here some confusion, by the way. Confusion is everywhere. How do we calculate evapotranspiration from vegetation, given the fact that vegetation is not alone out there? It is together with some land, right? Only in the Amazon can you find 100% cover, vegetative cover. But in most areas, most temperate areas around the world, you will not find 100% vegetative cover, canopy cover. So if you have a mixed situation, then it's going to be difficult for us to determine which part are we calculating under the assumption of evapotranspiration through the plant, and which one I am not calculating. And since that is an impossible task, what we normally do is we say, if there is land where you're going to calculate evaporation, particularly from a desert or from a lake or a reservoir, you can use an evaporation formula. But if you're looking at an ecosystem which has everything, you're going to refer to that formula as evapotranspiration. In other words, if there's an ecosystem or some plants out there, no matter how small percentage, nobody's ever figured that out, then we refer to that calculation as evapotranspiration. And that's why it says in here, the whole thing is called evapotranspiration. Now, transpiration, though, is the process by which plants transfer water from the root zone to the leaf surface. where it eventually evaporates into the atmosphere. I have a couple of minutes in here. The process by which transpiration takes place can be described as follows. And I'm going to have you read this green box in here. It has to do with plant physiology. So as you can see, a lot of the stuff we do in evaporation gets into plant physiology. We are typically not experts on plant physiology, certainly not. Very far from that. But yet we got to at least physically or chemically understand the process. And the process is more or less like this. There is osmotic pressures that allow the plant, or rather the water to move from the root zone. The water has to be in the root zone. And then it is pulled up like pumps, pulled up like through the stems, pulled up and deposited right next to the leaf. And once it becomes next to the leaf or within the leaf structure, then there are these stomata. They're called openings in the leaves that allow the water to seep through and become available for evaporation. That's the process. How do these stomata look? There's a picture in there, stoma. It's called stoma in a tomato leaf seen through an electron microscope. Very small, only seen through a microscope, but where the water can escape. So, therefore, a plant is always losing water. Always losing water. Why is it losing the water? Because it needs the water to transport the nutrients to the plant itself. The plant is demanding nutrients in order to do the fruit. If you're going to if the plant is going to produce the fruit, it requires nutrients. And where are the nutrients going to come? From the soil. The soil would have to either have the nutrients, or you would have to add the nutrients by way of fertilizers for them to be lifted up by this process, by this osmotic pressure that lifts it up. But by the time it distributes and delivers the nutrients, the water cannot go up. Cannot go down. It has to keep going up until it actually is evaporated through the stoma. That's the process that happens in every plant. Every plant has this procedure. So that is where I'm going to stop in here. We reach our time limit, 6:45, right? 6:44 right now. So please read this stuff again, because I know for many of you, some of what I said today is confusing, and I don't blame you. Sometimes it's confusing even for me, and I've written this stuff and I've studied this and taught it for 30 years. Okay? So we get there, we're going to stop it here and figure 225, and we'll continue next Wednesday. That's when our next class is going to be. Okay, well, thank you. Any questions? I'm going to cut it at this point. Okay, bye-bye. We'll see you next Thursday. I'm sorry.
Bye.
See you Wednesday, not Thursday.